Today's topic is Nodal Analysis, Part 1. And let's think of it in context of all our circuit analysis tools in our toolbox. The various circuit analysis tools we've discussed so far in the course, like voltage divider rule and current divider rule and finding total resistance, all of these methods are shortcuts to solving for voltages and currents in a circuit. Now they're useful, but it requires us to look at a circuit and see the pattern. But what if you can't see the pattern right away? Is there a surefire method to solving for any voltage or any current in any linear circuit? Well, the answer is yes, and it's an algorithm we call nodal analysis. So here you take any circuit, and if you follow the steps in the algorithm shown here, it yields a system of equations where you solve for all the node voltages in the circuit simultaneously. So before we begin following through those steps, let's begin with a review. Now, we define an element as a single two-terminal symbol in a circuit. An example might be a voltage source or a current source or a resistor. We define a node as a point at which two or more elements have a common connection. Now we think of that node as a single electrical so-called location, or it could be a point or a line in this circuit, and it has the same potential or voltage. The locations occur between at least two elements, and these lines between elements represent perfectly conducting wires. So I have a circuit here, and I want to know how many elements are in this circuit. Well, I can see I have a voltage source here, 6 volts, and a 12 volt voltage source there, and 3 resistors. And all of those are elements because they are a single two-terminal symbol in a circuit. The two terminals are shown here and here. That's a terminal, two terminals, and so forth with all these elements. So we say that we have a total of 5 elements. 2 of them are sources and 3 of them are resistors. Now, how many nodes do we have in this circuit? I'm just going to go ahead and erase all this so that we kind of show it clarity. Well, again, a node is a point at which 2 or more elements have a common connection. Okay, so here's a common connection between the 6 volt voltage source and the 4 ohm resistor. So this is a node. I also have a connection between the 4, 3, and the 8 ohm resistors, and I'll label that here, and that's another node. I also have one between the 8 ohm resistor and the 12 volt voltage source. And finally, I have a connection all the way down here at the bottom between the 2 voltage sources and the 3 ohm resistor. So the total number of nodes we have is 4. One of them we'll define as ground. Okay, now that we've discussed the definitions of elements and nodes, let's follow through with the steps 1 through 5 to solving a circuit using nodal analysis. The first step is to label the nodes. Okay, so just as we've shown above, I have node A between the 6 volt and the 4 ohm resistor. I have B and I have C, and I also want to select one as ground. So those are A, B, and C are nodes, and the ground node is down here at the bottom, and I'll label that with the symbol for ground. And I'm done with step 1. Step 2 is to assign the voltages and identify known and unknown voltages. Okay, well in this case what we're looking for are the voltages at each one of the nodes. So VA is equal to, well, let's see, the bottom side of this voltage source is at the ground. The top side is a plus, and that's located at A. And the potential between the ground and voltage at node A, is 6 volts. So I'm going to say that VA is 6. VB, if I look at it in the circuit, I see that it's connected to 3 resistors. That's the node that's connected to the 3 resistors. And I don't know right off the bat what that voltage is. So I'm going to say at the beginning of the problem, this is unknown. Now let's take a look at the voltage at C. What is the voltage at C, at node C? Well, again, if this is the negative that represents the ground point, the plus side is at the node C, and the potential across that from C to ground must be 12 volts. So I know what that voltage is. And then finally, if I want to be very specific, the voltage at ground is defined as 0. So of those 4 nodes, how many of them are unknown? Well, it's only the VB, and that's my unknown node voltage. And I'm done with step 2. Now, let's go on and look at step 3. Step 3 is to label the currents and apply Ohm's law. Okay, so here's the step where we define the direction of the currents. And here's the rule of thumb. Assume a direction. And that's it. We assume a direction for a current. I1, let's say, is going from the node B to node A in this direction, from B to A. Current I2 is going from B to ground. And current I3 is going from B to C. Okay, so in this case, we've defined it in that direction. Could I have defined them in the opposite direction? Absolutely. And when I solve the problem, let the math do the work. And if the currents turn out to be negative, then my assumption was just wrong. It was just opposite of what I said. So as long as you have the direction of the current in your circuit, and you follow the process, do the math at the end, and the value is negative, then I can see clearly that based on your circuit diagram and the direction of the current flow, the current is just simply flowing in the opposite direction. So a negative value for current is just fine. Okay, so now that we've identified the currents I1, I2, and I3, we want to apply Ohm's law. And basically what that means is we want to define the current in terms of node voltages. So what does that look like? Well, V equals IR. That's Ohm's law. And if I solve for current, I is equal to V over R. Okay, well in this case, what is the voltage for I1? Well, if I go down here and I see that, I1 is equal to the voltage at B going from to. So it's going from VB to VA. So I'm going to subtract those two to find the voltage across the element 4 ohms divided by the value of 4, and that's equal to I1. Now, to find I2 is simply equal to the voltage at VB minus the voltage at ground, which is 0, and I divide it by 3 ohms. So here is I2, VB minus 0 divided by 3. I3 is equal to the voltage across the 8 ohm resistor, and it goes from B to C. So the current is equal to VB minus VC divided by 8. So that is my application of Ohm's law for step 3 to label those currents. Okay, done with step 3. Next, I'm going to say that we want to apply Kirchhoff's current law at the nodes with unknown node voltages. Now, this is where we may need to go back and take a look at what my unknown node voltages are. And we've identified V sub B, VB, as the unknown node voltage. So I'm going to apply Kirchhoff's current law at node B. And I say that in this case we'll have a minus current going out of the node and a plus current going into the node, and I sum those up and I set it equal to 0. So in this case I will have minus I1 minus I2 minus I3, because they're all going out, is equal to 0. Now I know in my mind I'm thinking I just labeled it that way, so I'm sure that one of them must be negative, because in order to have a sort of a balance of currents going in and out, I have to have one of the currents at least going in. But again, that's okay. We just label them and then let the math do the work. So if I multiply through by minus 1, I get this equation here. Now, so I'm done with step 4. That's it. Applying Kirchhoff's current law to the unknown node voltage, node B. Okay. The next thing I do is substitute and solve. So in this case, I1 is shown here, and I apply that to my equation for Kirchhoff's current law. So here's my I1. Here's my I2. And here's my I3 right here. And I set that equal to 0. Now, solving, I'm just going to go ahead and do a little bit of algebra and say VB divided by 4 minus 6 over 4 plus VB divided by 3 plus VB divided by 8 minus 12 over 8 equals 0. Combine like terms, I get 1 over 4 plus 1 over 3 plus 1 over 8. V sub B is equal to 3, and VB is equal to 4.24 volts. And there's my answer. Now I have, if I go back to the beginning, I have a circuit here where I know what voltage at VA is. I know what the voltage at VB is now, and VC. And because of that, I can come in here and see that all of my currents here are defined in terms of node voltages here. So I can solve for any one of those currents as well. As long as I have all the node voltages, I can find currents in every one of those paths. And that's it. That's the process for nodal analysis. Let's do another problem. Here's an example where I have, it looks similar than the other one, where I have, looks like, how many elements do we have in there? Well, let's take a look. 1, 2, 3, 4, 5. 5 elements, where 2 are sources and 3 are resistors. How many nodes do we have? Well, again, node A, node B, node C, and then this is ground right here. So there are 4 nodes. Now I'm going to erase this because it gets a little confusing when I start drawing in currents. But that's it. So we have 4 nodes. One of them we have to designate as the ground, which we've shown right there. That's my ground. So I'm going to label nodes and the ground. Step 1 is complete. And I'll put a parentheses around the A, B, and C just to be specific and notify us that those are nodes. Label nodes and ground. Step 1 is complete. Step 2 is to assign voltages, and we want to make note of which ones are known and unknown. So let's assign the voltages. VA is equal to what? Well, again, here's my 6-volt source. The minus is on the node, the ground node, and the plus is on the side of node A. So the voltage between the ground and node A is equal to 6 volts. VB is equal to And again, this is an example where I have 3 resistors that are connected in one spot. That's a node at node B. And at the start of the problem, I don't know what VB is yet. VC. Now notice this. Notice the polarity of this voltage source. The plus is at the ground, and the negative is at C. What this means is that the node at voltage C, or the voltage at node C, is less than 0. It's less than the potential at ground, and so this V sub C is equal to minus 8 volts. Notice the polarity. Okay, and we also want to identify which ones are known and unknown. So VB is my unknown node. So I'm basically going to have one equation and one unknown, and I'm going to solve for VB at the end. Okay, done with step 2. Let's go on to step 3. We want to label the currents and use Ohm's law to define those currents in terms of the node voltages. Okay, let's define those currents as I1, here's I1, here's I2, and here's I3. Okay, so I1 is equal to the potential at B to the potential at A. Notice here that the direction of the current is from B to A. So I go VB minus VA divided by 4 ohms. That's Ohm's law, V over R. I2 is equal to VB minus the voltage at ground, or 0, divided by the resistance between those 2 points, which is equal to, or those 2 nodes, which is equal to 2. I3, oops, don't want to put a line on top of that. I3 is equal to the voltage at B minus the voltage at C. We're going from the voltage at B to the voltage at C, divided by 8. And that's my current equation in terms of the node voltages. Okay, done with step 3. Step 4 is to apply Kirchhoff's current law at the nodes with the unknown voltages. Okay, well, where are they, or which ones are they? Well, it's just at node B. So I'm going to apply KCL at node B. So I'm now going to look at the currents I1 and I2 and I3, and I'm going to add the currents up. So I notice also that all my currents are going away from node B, and so they're negative. So that's a minus I1 minus I2 minus I3 is equal to 0. Or, if you like, I1 plus I2 plus I3 is equal to 0 if I multiply through the whole equation by negative 1. The last step is to substitute and solve. So I take step 4 and substitute in step 3. So I1 is equal to VB minus VA divided by 4 plus I2, which is VB over 2, plus I3, which is VB minus VC divided by 8, and I set that equal to 0. Doing the math, I'm combining like terms. I could see that VB is equal to 571 millivolts, and you can solve that just to verify that that is correct. Now, the second part of the question is this. Now that I have the voltages at node A, node B, and node C, I want to find the current I unknown in the circuit above, assuming that I unknown, I unc, points from C to B, node C to node B. And I'm going to use a different color here to show that we are going from C to B, and I'm going to put my arrow there, and I'm going to call that I unknown. Now it could be any variable. IA, not IA, it could be IG, ID, IE, whatever. We're just going to call it unknown. And unknown is defined from C to B. But if I look at my drawing, I see that I unknown is just the opposite of I3. And I've solved for, and I know my equation for I3, which is right here. So I'm going to say that I unknown is equal to minus I3, which is equal to minus VB minus VC divided by 8. And VB is equal to 0.571 volts minus VC. And VC is also a minus, so that's a minus 8 divided by 8. And therefore, oh boy, what was that? Therefore, I unknown is equal to minus 1.07 amps. That's my answer. Let's do one last problem. I'm going to move down to page 5 of your notes. And let's do one last problem. And I see here that I have added another node. Interesting. So let's take a look at this. We're just going to solve for I unknown in the circuit below, and we're going to use nodal analysis. Okay, so the first question I want to ask is, how many elements are in the circuit? Well, there's again 2 voltage sources and 4 resistors. So 1, 2, 3, 4, 5, 6 elements. How many nodes are there in the circuit? Okay, well, they're actually labeled here, which is nice. But I see that I have node A, node B, node C, and notice that D is the same. This is at the same potential. And I have this ground plane right here. Okay, so we actually have the same number of nodes, 4. 4 nodes, 1, 2, 3, 4, where C and D are the same potential. Okay, so now that we've sort of analyzed the circuit and see where our elements and our nodes are, let's label the nodes and reference. So here's A, node B, node C, and node D. Also, we have ground down at the bottom. So there's my reference. Next thing I want to do, and I'm done with step 1. Next I want to do is I want to assign the voltages and identify the known and unknown voltages. All right, so let's take a look at what VA is. VA is equal to, well, again, the minus is at the ground and the plus is at the A. So the voltage from A to ground is 5 volts. 5 volts. The voltage at B, V sub B, is equal to, well, let's see. I've got another 3 resistors, 1, 2, 3, that are connected at node B. And so I don't know what the voltage at node B is at the beginning of the problem. So I'll say unknown. Voltage C is equal to, well, I see that this is the same, that voltage at C is the same potential at D because it's just a straight line here and there's no element in there, so it's the same potential. And the potential at D is, well, let's take a look at that. I have the minus sign down here at the ground and the plus side is at node D. So the voltage from node D to ground is 10 volts. And finally, let's take a look at what the voltage at D is. Voltage at D. Well, again, voltage at D is equal to C, so that's 10 volts for the same reason as I mentioned before. So I'm done with step 2. Step 3 is to label the currents and define those currents in terms of the node voltages, and we're going to use Ohm's law to do that. So in this case, I1, I will define in this direction. Let's see. Let's go ahead and take away some of this. Put this back, put that back. Okay, so let's label them. I1 is going this direction. I'll call that I1. I2 is going from node B through the 20 ohm resistor, and I'll call that I2. I3 I'll show in this direction from B to C, and that I will call I3. ID, or I4, is through the 8 ohm resistor, I4, and then finally I5 is going through that path from C to D down to ground. That's I5. Okay. I1, oops, let's do it this way. I1, thank you, equals from B to A, VB minus VA divided by 15. I2 is equal to, well, from B to ground. That's the direction of my current, so I'm going to say VB minus 0, because the potential at the ground node is 0, divided by 20. That's the resistance between those two nodes. I3 is equal to, well, the voltage at B minus the voltage at C divided by 30 ohms. And I4 is equal to VC minus the potential at 0, or at ground, which is 0, divided by 8, and I5 is unknown. Okay. So I don't know what the voltage is through that path with the voltage source, the 10 volt voltage source. Okay, so now I've labeled all the currents. I'm done with step 3. Step 4 is to apply KCL at the nodes with the unknown node voltages. Okay, where are they? Well, it's just at VB. I know what VC is, and I know what VD is. So I just want to find the KCL at node VB. That also tells me, because there's only one unknown node, that I will have one equation and one unknown. Okay, so now I will solve for that. So the current at node B. Well, I'm going to say that it's going to be minus I1 because it's going away from node B, minus I2 because that current is going away from node B, and I3 is also going away from node B, so I'll say that's I3 is equal to 0. Another way of saying that is I1 plus I2 plus I3. This makes it a little bit cleaner when we substitute and solve and set it equal to 0. Now, if I wanted to, I could also say that the KVL or KCL at node C is going to be I3 minus I4 minus I5 is equal to 0. And we might need that later, so I'll just put that in there. But what we really want is the KCL at node B. Now what I want to do is to substitute and solve. Okay, so let's take a look at the equation for I1 is VB minus VA divided by 15 plus VB over 20 plus VB minus VC divided by 30 equals 0. Now notice that I've defined what VA is and VC. And I'll just write it in there on the top. So VA is equal to 5 volts. And VC is equal to 10 volts. So there's really only one unknown variable in that equation. Now I'm going to just solve it algebraically. And when I do, and you can check my numbers on this, V sub B is equal to 4.44 volts. And that's my answer. Now, I'm going to go back and ask the question then, what is I unknown? I unknown is the opposite of I3. So again, I'm going to say that I unknown, what I want to find for the whole problem, is equal to minus I3, which is equal to minus VB minus VC divided by 30. Now in this case, I now know what VB is. I just solved for it. I know what VC is, shown up here, the 10 volts. And so I have the value for I unknown, which is 185 milliamps. And that's the answer. Now we know how to solve for any voltage or any current in any linear circuit using nodal analysis.